It's our great pleasure to introduce our energy faculty candidate today, Jason Quinn. So Jason actually did his bachelor's degree here at Colorado State University, and then he went on to University of Wisconsin, got his master's degree actually in nuclear engineering, and then came back here to get his PhD. He started here in what it would have been fall of 2008, something like that. And then actually at a time when algae biofuels were really taking off, he did his PhD jointly under Brian and Tom Bradley. And in fall 2012, started a faculty position at Utah State, tenure track faculty position. He's been on the faculty there for 4 years. And I know from experience he's built up quite a reputation in the field, particularly when it comes to techno-economic and life cycle analysis and things of that nature. So, I'll go over to Jason.
Thanks, Anthony. First of all, I'm grateful for you all taking the time to come here and listen to my presentation. I divided it into two aspects. One that focuses on the research, and in the latter part I'll talk a little bit about my teaching philosophy and interests here at Colorado State. So I'll start with the research, and so specifically I've got two core aspects. One's in experimental systems, and then the other part is in engineering process modeling for life cycle, techno-economics, and resource assessment. Before I get started, I'd like to specifically acknowledge and thank the funding agencies that have supported a lot of the work I'm going to present on here. It ranges from private companies to government agencies, also the state of Utah. This work wouldn't be possible with all the graduate students I've had the great fortune to work with. It's an aspect that I truly enjoy. And what's been really exciting also is the work that some of the undergraduate students have been able to produce as well, and I'll be presenting some of that work here as well. And then lastly, a variety of collaborators that I work with, ranging from other academic institutions, private research entities, as well as a variety of different national laboratories. So with that, what I'd like to first do is give a general overview of the research that I do, and then I'll talk about the different technologies I've been able to effectively apply this research model to. So at the core of this is system modeling. The system modeling integrates sub-process models into a system-level process model. It then is, first of all, modular construction, so you can evaluate different processing technologies on a systems level. It's rooted in engineering, so it's high fidelity, and then it's operated at multiple scales, so ranging from the laboratory scale to pilot plant up to the end plant is kind of how those systems are integrated. Directly coupled with this is experimental systems. And so experimental systems, the first flow in is for model validation. And so those experimental systems are typically being constructed in a fashion that facilitates the extrapolation of the data up to these large scales. Now concurrently through the system modeling work, a lot of times there's the identification of data gaps, process feasibility, for example. And so that information is feeding back into the experimental systems to identify areas that might need to be further explored. On top of this foundation is the sustainability modeling. And so that couples not only life cycle assessment and resource assessment, but also techno-economic feasibility. And a critical component here is the data feedback from this modeling effort down to the experimental systems. And so enabling to highlight areas or decrease the experimental space through identifying topics that might expedite commercial viability, for example, is really important, because then you can strategically spend resources in the experimental side of things. And so then the data feed loop comes back around, and then I evaluate the impacts that are associated with the improvements made in the laboratory. And so that's kind of a general overview of the work I do. And then here's a variety of different technologies I've been able to apply that model to. So as Anthony talked about, I've got a core expertise in microalgal biofuel systems. Right below that, I've expanded into yeast systems, not only for biofuels, but also for bioproducts. We've looked at direct coupling, renewable technologies, water pumping, and desalinization. And then also started to evaluate nuclear power systems, specifically looking at small modular reactors. Also expanded work into looking at wireless power transfer for the electrification of transportation. And then lastly, the evaluation of synthetic spider silk. So based on time, I'm going to talk about three of these in at least a high level of detail, and then just kind of briefly touch on the other three. My intent here is to just kind of illustrate how the work that I do can be leveraged by these different technologies, and the work I do isn't necessarily limited to these technologies. So with that, I'll start with the core expertise I have in microbial systems. So as I talked about, I'll come back to kind of this overall schematic. This one's specifically applied to microalgal systems. And so system modeling and engineering systems are directly coupled, and I'll use the research I do to illustrate this. And so I'll first talk about the experimental systems, but the experimental systems that we developed were specifically identified through the system modeling. And so with algal systems, you need a carbon source. And so a lot of the system modeling work that's being pushed forward is going to integrate industrial waste carbon. So coal-fired flue gas, for example, is the carbon source. And so all of the models assume co-location for one, and two, that it's a seamless integration. And that there isn't, there's no complications associated with that. And so that's one of those things that as I started to think about that, I was like, gosh, is that true? And so I wrote a proposal to the National Science Foundation to say, hey, listen, we want to understand really what the impacts are of integrating with industrial flue gases on algal productivity, and more importantly on the downstream processing and how it impacts those products. And so that proposal was written and it was really focused on experimental work. And so what I'm presenting here is on the left is upstream side of things and then downstream side of things in blue. And then highlighted in red is the experimental work that I'm talking about in terms of coal flue gas. All the other boxes are illustrated here are experimental systems that I currently work in, but don't necessarily have time to talk about. And so there's a lot of work ongoing in terms of growth evaluation on productivity, for example, on the upstream side of things. And on the downstream side of things, I'll talk a little bit of detail in terms of the conversion to biofuel, biofuel intermediates, as well as bioproducts. And so the coal flue gas represents just a good example of how all of this ties together. And so through this proposal, what we were really focused on was understanding first the upstream side of things, the impact of these heavy metals. And so to give a little bit of background, coal has heavy metals in it. As that's combusted, a huge fraction, over 99% of the ash is captured, but there's a small fraction of fly ash that goes out the stack. And so if you integrate that in with a cultivation system, you're ultimately going to be introducing heavy metals into your cultivation system. And so how does that impact A, the productivity, and then B, the downstream processing of that biomass? So specifically looking at, do you now have a contaminated biofuel that you can't even use because of the heavy metal contamination? And then bringing it full circle, directly integrating these results into modeling work to then assess and understand the scalability of the system based on this experimental work. So strategically developing experimental systems, so the reactors, for example, they are indoor photobioreactors, but they're operated at high light. And they're operated on a 12-12 duty cycle, so we're trying to at least make approximate how things would operate outside so we can integrate this into large-scale models, which has been a huge gap previously in the work because it's all very low light, very low concentrations, and so again, you can't scale that data up into the modeling work. So jumping to the results of the upstream side of things, what's presented on the vertical axis is growth density in grams per liter, horizontal axis is time. The top line is the control, no contamination. The bottom line represents integrating these heavy metals. And so you can see here there's a dramatic impact on the overall productivity. Well, if it's a biofuel system, you really want to look at lipid content combined with that. So the first bar is the control, the second bar is the contaminated. You combine these, you're looking at over a 50% decrease in the overall lipid productivity. Well, when you're starting to look at economic viability, life cycle impacts, that's your functional unit. You've taken a huge hit. So what was originally assumed, a seamless integration, actually represents a 50% hit on your production of your system, which is detrimental to the overall economic and life cycle impacts. Now concurrently, and more importantly, we understand where are these heavy metals going? Are they actually integrating, being attached to the biomass? And so through ICP-MS, we can quantify exactly where these heavy metals are going. So the green bars are the ones to specifically pay attention to. That represents heavy metals that are in the biomass, or either surface bound or actually sorbed into the biomass. And so there's a significant fraction, and that can now potentially limit the downstream processing. So we evaluated the processing of the biomass into biofuel through an acid in situ transesterification, as well as through a supercritical methanol conversion. And so again, looking at what was interesting was that there wasn't a statistically significant difference in the overall yield out of the systems between control and contaminated, mainly because those two processes are very robust and they're good at cracking cells and other things, that they're very violent. But more importantly, looking at where do the heavy metals go in the products again. And so the green bars here represent where the lipid extracted algae. So a lot of the economic analysis show that you need a high-valued product in a algal biorefinery in order to make it economically viable. On a positive note, the red bars across the bottom that barely show up show the metals that will be transferred to the fuels. So it looks like from this work that the fuel is not being contaminated by the metals. The large fraction is going with the methanol water fraction, but there's still a significant fraction that's going with the biomass. And so following on to this work, integrating the modeling, understanding how does this impact the end use of these systems. We looked at the specific metals, so there were 14 metals. I just pulled one metal to illustrate this. The horizontal bar, or the dotted lines, represent different regulatory limits on metal contamination. The 1x, 5x, and 10x represent different starting metals concentration in the algal growth system. And the two different colored bars represent surface bound in the blue, and then in the green, actually sorbed metals into the biomass. And so as you can see here, you start to see, even at the 1x level, there's limitations in terms of regulatory, what you can actually use the biomass for. And so this is directly going to impact the overall economics of the system. And so there's similar results for the other 14 metals. The bars just kind of shift in different directions depending on what the results are. And so what I've intended to do here is just use this one specific example to illustrate how all of this kind of comes together, and working in a variety of other areas that I'll briefly talk about. But again, being able to establish the experimental system strategically to inform models, and more importantly, taking information from the modeling work to identify data gaps in terms of process integration, for example, experimentally determine what those are, and then ultimately perform the sustainability assessments. And so in terms of future direction and areas that I'm interested in continuing to move forward in, the process demonstration is something that is critical. A lot of seamless integration assumptions are being made. And so, for example, I work with Sandia National Laboratory right now. They're doing hydrothermal liquefaction, and there's a high concentration nutrient stream that's seamlessly integrated back into the growth system. Well, is that true? Is all of the nitrogen that's in there bioavailable nitrogen, for example? And so there's opportunity to evaluate that recycle stream and that process demonstration. Also looking at evaluating, they're doing a fractionization process. And so again here, there's a nutrient-rich stream. Can you integrate that with a yeast system, for example, to produce a high-value protein product instead of integrating that back in with an algal system? I've done a lot of work in growth modeling. It's part of my dissertation work with Solix. There's a huge opportunity for open raceway pond growth modeling and optimization. That's an area I'm specifically interested in exploring. Specifically looking at species characterization and moving into high temperature thermophiles, for example. Looking towards culture robustness, and there's areas to explore in that. The system modeling work we've done, we've identified some data gaps that are very pure and simple mechanical engineering challenges that can be answered through mechanical engineering. So that's CO2 uptake efficiency, for example, as well as looking at the efficiency of delivering mechanical power to fluid power in raceway ponds. And so what's being pushed forward right now, there's a lot of large uncertainty there, and those two specific areas represent critical inputs in terms of energy requirements for the overall production process. Currently working to develop preliminary data with produced water and how that impacts productivities. Specifically looking at Uinta Basin produced water with the oil and gas industry. There's a lot of this that's being produced, and so algal systems could serve as a dual purpose in terms of synergistically remediating water. They're a water-intensive technology as well. But also looking to integrate with other waste streams as well, characterize these experimentally. In terms of funding mechanisms, currently I've got a collaboration that's ongoing with Sandia National Laboratory on a modeling side of things, but that's also extending and hopefully moving towards experimental work. There's opportunity to work with a couple of different companies out there, as well as a variety of government agencies in terms of some of the fundamental research that I'm interested in continuing to push forward on. So that's kind of a general summary for the experimental side of things. What I'd like to talk about and illustrate now is the system modeling work that I do. And so I talked a little bit about the experimental systems that's used to generate data for validation. Concurrently, do work in Aspen, and that's a way to kind of initially develop validation data for modeling work outside of the laboratory. It's a very powerful chemical engineering platform that we've been able to leverage specifically with the Sandia National Lab project, as well as a couple other different projects. When you look at the system model, I'll come back to this schematic because there's an upstream and downstream. And so the modeling work is being constructed modularly in fashion, and that's very powerful because it enables you to first define a baseline pathway, for example. So what I've illustrated here in the grow system is an algal turf scrubber, and this is work with Sandia National Lab, and I'll talk a little bit more in detail about that technology, with the thermochemical conversion through HDL. And so this is work we've done with them to directly understand this specific process. Well, they're moving towards a fractionization process, and so because this is built modularly, it's a plug-and-play process. So you can plug out a different technology and then understand on a systems level how that impacts energy and mass flows and directly compare that to other technologies. Now concurrently, the entire industry is pushing forward on open raceway ponds, and so plug and playing in an open raceway pond on the upstream side of things such that now you can directly evaluate the fractionization process agnostic to the growth system is a very powerful tool. And so having these models constructed, it's very easy to work with various partners and directly understand their technology and the impact their technology can make on a systems level, which is critically important. And so again, that system modeling work I presented here really represents this foundation for the sustainability modeling work that I do. And so the primary outputs from the system model represent primary inputs into the sustainability assessments for life cycle assessment, techno-economics, and resource assessment. And so what I'd like to do now is just briefly talk about those three areas. And so in terms of life cycle assessments, what I've illustrated here are 5 different life cycle assessments that I've done recently with the partnering institutions highlighted in the corner. The blue boxes really highlight downstream processing technologies that were being evaluated, and then the green ones are more focused on the upstream cultivation side of things. Also done a variety of work in the techno-economic field, primarily partnering with Sandia National Laboratory for that, evaluating the different processes that they're pushing forward, primarily out of their 2 laboratories in California and New Mexico. And so I don't have time to go into all of these, obviously, but I would like to kind of highlight and illustrate how this work comes together. So I'll talk about the algal turf scrubber system as an example. A lot of times these systems are directly coupling life cycle and techno-economics, so I'll just pick one and do techno-economics, the other one and do life cycle. In terms of the scope of this work, it was to directly assess and compare 2 different productivity technologies. So on the far left here, this is an open raceway pond, a traditional pond system. On the far right, an algal turf scrubber system. Each of these systems have advantages and disadvantages, and the work that we do is really intended to capture those advantages and disadvantages and directly compare them on a systems level. And so without going into too much detail, the algal turf scrubber system is a native culture. It's a more robust growth platform. Open raceway ponds are homogeneous, higher lipid content. There's a variety of other advantages and disadvantages we can talk about. But coming back to the foundational system modeling, there's upstream and downstream side of things. The system boundary, initially we strategically drew that around just the cultivation systems to directly understand what the cost associated with the production of biomass was. This represented a huge data gap in the DOE portfolio for one. And so with this, we were directly comparing these 2 technologies, which represented the algal turf as well as the open raceway pond, and then defining 3 different scenarios so that we could understand where we are today and where we expect to get kind of where a near-term realizable, if you will. Well, the entire industry reports all costs on $1 per gallon. So we extended the system boundary to include a conversion metric, specifically looking at hydrothermal liquefaction as the downstream processing component, such that again we can expand that out to directly compare it on a slightly larger boundary. So there's a lot of assumptions that go into this work, a lot of modeling work, and so I'll kind of jump directly to results. And so the first one is the cost dollars per ton for the biomass for the 3 different scenarios that we were looking at, broken down just into general, capital, operational, and tax. And so each of these big categories has a variety of other breakdowns such that we can identify areas that are high cost drivers, for example, in these scenarios. And so that's what's illustrated in a little bit more detail here for the baseline scenario, is breaking down the operational capital and then the total cost associated with the production. In this case, with the total for the biofuels. When you look at the first one, an algal turf scrubber system for the baseline scenario, which is in the middle, is more promising. It's got a higher productivity, it's a more robust culture. When you convert it into fuel, because of the high lipid content that's associated with an open raceway pond system, it's actually a lower dollar per gallon for the total cost, down around the $4.50 mark. And then when you add in all of the capital and everything else, that jumps up to the $6.50 mark. And so one of the great things about this work is through sensitivity analysis, DOE has a target of $3 per gallon gasoline equivalent. We can feed back to Sandia realistically and run all these other scenarios that says to get to $3 per gallon, these are the improvements that you need to make, and this is the research areas that you need to target in order to reach that DOE production target cost number. And so in terms of life cycle assessment, I'll jump over to work that I did with Idaho National Laboratory. As I said before, with Sandia Project, we're concurrently doing life cycle assessment on those systems as well, so we have results for that as well. But this was just a way to illustrate, again, a system process model looking at 2 different thermal-chemical conversion systems. And so what I've highlighted here is just the bio-oil recovery, and that even these sub-processes have a high level of fidelity that break down into multiple sub-processes integrating together. And so, we started to initially model this at lab scale and scaled that up to production scale. So now all of a sudden you're looking at material recovery, heat recovery, really looking at the petroleum industry as a model for that. And so we were directly comparing hydrothermal liquefaction and pyrolysis as the 2 thermal-chemical conversion processes. In terms of life cycle impacts, we quantify that in 2 ways. The first one being a net energy ratio. What's being illustrated here in the first set is pyrolysis, the next is HTL. And the 2 different bars represent the 2 different systems, one the experimental side of things, and then when you start looking at the industrial scaled system. To directly compare to traditional fuels, the bottom black line is the conventional diesel, the top one is the soy-based biofuel. Conventional diesel represents the gold standards. It's very challenging to meet that. Having net energy ratio greater than 1 is obviously not desirable, but it is sometimes tolerable because of the form of the energy that is being converted into. Jumping over to the global warming impact potential, on the far right-hand side is the conventional fuels, and then the HTL and the pyrolysis pathway. Well, in the middle of the pyrolysis pathway, you see this large blue bar. That large blue bar is natural gas input. Pyrolysis requires a dry feedstock, and so that instantly represents a non-starter for algal systems. And so these results show that in terms of global warming impact, I should state the system boundary here is just a welded product. To get to a welded wheels, you add the combustion of the fuel, which is about 70 grams of CO2 per megajoule, depending on the vehicle you're running in. And so very quickly you can see that pyrolysis pathway will not meet the renewable fuel standards, as it's not a 50% reduction in greenhouse gases. Whereas the HTL pathway, the way it's been modeled here, will meet that renewable fuel standard, which is important. So again here, being able to understand and illustrate how these 2 different thermochemical processes, the advantages and disadvantages, and highlighting where things are going wrong, if you will, in terms of environmental impact. So the next thing I'd like to briefly talk about is some of the resource assessment work that I do. So again, this is all building off of system modeling. So this is coupling and integrating biological growth modeling with GIS information data systems to directly understand productivity potential. So the biological growth modeling integrates hourly meteorological data to understand what that productivity looks like out of your algal biofuel systems. So initially we did this looking at just land restrictions in the United States, which is the first one. We extended that work to be a global assessment. Very proud of that work. That work was published in the Proceedings of the National Academy of Sciences, directly looking at the productivity potential and land resource available across the globe in terms of microbial biofuel systems. Through the system modeling work, again, identifying that CO2, we're just going to co-locate. Well, when you start co-locating, what are those limitations in terms of scalability? Economically, what are the limitations in terms of pumping CO2? And so, again, that work dramatically decreases the total amount of fuel that can be produced in the United States, for example. And then lastly, this just looking at the overall yield that you can produce in terms of resource. So a lot of people claim we're just going to use nutrients from wastewater. Well, depending on your pathway, the dotted line there represents the 2030 DOE fuel goals. U.S. wastewater is not going to be the answer in terms of productivity, in terms of meeting all of your nutrient requirements to meet those goals. In fact, this could even potentially put a strain on U.S. fertilizer production, for example, depending on what pathway you're pushing forward in terms of scaling microbial biofuel systems. In terms of future directions and interest on the system modeling and sustainability effort, I'm interested in continuing to evaluate alternative process technologies. There's advancements that need to be made across the board in terms of microbial systems, and being able to understand and evaluate those impacts are important. Technoeconomics and life cycle represents really a requirement for all large consortium funding that comes out of DOE. It's a model for ARPA-E. And so, this work is valued and it's a requirement for a lot of the large consortiums. I'm continually partnering with National Labs, NREL's India National Lab on proposal efforts to be performing a lot of this work. I'm interested in concurrently developing a sustainability metric where you start integrating not only economic viability but life cycle impacts as well to concurrently have results on those fronts. And kind of long off is we've got a very good understanding of the time value of money, but there's very little work being done on the time value of carbon. And that's something that's kind of a long shot out there, but something I'm really interested in kind of exploring. Lastly, I'm working with the VITO Algo Program Director. I identified some significant errors that PNNL has made in some resource assessment and trying to resolve that. And so that there should be some opportunity to continue on resource assessment from that. Currently, I've got multiple proposals pending for a lot of this work. There's 2 DOE proposals pending. I've got an NSF proposal pending, all focused on life cycle and techno-economic work. I've currently got work ongoing with Sandia National Laboratory in terms of performing economic and life cycle work with some of the downstream processing technologies that they're pushing forward. So that's a summary of the biofuel systems. And so what I'd like to do is use 2 of these others and go into a little bit higher level of detail in terms of the work that I do and how the modeling work integrates. And so the first one I'd like to talk about is wireless power charging for in-motion charging of electric vehicles. So this is a schematic that's intended to represent how the technology would work or be deployed. So the idea here is that you've got primary coils that are embedded in the roadway, and you've got secondary receiver coils that are on the vehicle. The vehicle's an all-electric, battery electric vehicle, and so this is eliminating things like range anxiety because you're charging as you're moving down the roadway. And so there's a lot of unknowns associated with this. Specifically, the work that I'm working on is looking at the optimization of vehicle architecture, optimization of roadway infrastructure, and then based on that information, understanding not only the economic viability of the technology, but the environmental impact, and also identifying this is where we need to be technologically for this to work. Similar to this $3 a GGE, this is the power transfer that's required to satisfy drive cycles, for example. It gets very complicated very quick because you're integrating drive cycles with GPS data and economic modeling. To illustrate some of the potential of the technology, if you take a Nissan Leaf vehicle and you put a 25-mile range on it, limit to that, and these drive cycles are limited to Southern California and Atlanta, but run 12,000 drive cycles through it, you're going to satisfy about 80% of those drive cycles. If you integrate 50 kilowatt charging just on the interstate systems and only the interstate systems, you very quickly are satisfying a very large fraction, up to 98% of those drive cycles through this wireless power inductive charging. And so it shows that this represents a very promising technology. More importantly, integrating this with economics. And so this is looking at overall operational costs associated with vehicles. So the first 2 bars are comparing an IC engine with a wireless power transfer EV on an interstate system. And then the next 2 are looking at the urban sector. So as expected, there's a significant savings associated with this. When you look at the life of the vehicle for a Class 8 truck, a semi-truck, for example, the amount of money that's saved in the operation of that vehicle at the end of the life of the vehicle, you can not only buy a new truck, but 3 more additional trucks, just in the amount of money that's being saved in terms of operation of the life of that vehicle. Taking this to a societal level, and this is a very complicated figure, so just give me a second to explain it. On the vertical axis is societal payback time in years, so in essence, there's a huge investment associated with the infrastructure required to deploy this technology. And then you're going to pay that back through energy savings associated with the operation of the electric vehicle compared to an IC engine. So on the horizontal axis, if you're a vehicle owner, you're going to expect to see savings. That's why you're purchasing this vehicle. And so the fraction that's not being dedicated to the vehicle owner is being dedicated to the payback of the infrastructure. So at a 20% payback, 25% vehicle owner savings, 75% of the energy savings are going directly to pay back the infrastructure. The 3 lines that are presented here represent different fleet penetrations of the vehicles. And so for our baseline case, when you look at just a fairly minimal fleet penetration of 10% and a 25% payback to the vehicle owner, you're looking at less than a 20-year payback on the overall technology. And that's very promising for something like this. And so, the work that we're doing here and the future work associated with this is we're looking at working towards coupling this with micro and macro network transportation studies, so being able to take the city of Denver, for example, through traffic patterning, developing macro and micro models, integrating that into dynamic vehicle models to then understand the deployment of the technology and truly what that infrastructure requirements look like. That's long-term vision, that's grand, global scale, if you will. On the small scale stuff, we're specifically looking at the deployment on small, closed campuses, so Department of Defense or airports, for example, and how this technology can impact those areas. There's a huge push in port authorities to go to zero emissions, so how can this technology be deployed there? Concurrently, we're looking at the environmental impacts, not just in terms of carbon, but criteria pollutants as well, not just in the operation, but also in the construction and the development of the technology as it's being deployed. Partnering with a variety of different people, there's a select center that's being launched at Utah State, and I expect to continue to work in that area because this represents a critical sales pitch, if you will, in terms of the promising of the technology. There's a variety of people pushing forward. There's actually a huge push in England, and there's an opportunity to potentially work directly with them. They're doing a huge pilot scale study, which would be really exciting to work with that. Currently have an NSF proposal pending to continue work in this area as well. So the last one I'd like to talk about in some level of detail is the work I'm doing in nuclear power systems, specifically small modular reactors. And so small modular reactors are, they range, typically a maximum size of small modular reactors, 200, 225 megawatts electric, and range all the way down to the 40s megawatt electric. And so what we are doing here is trying to understand the economic viability and the competitiveness of small modular reactors compared to large reactors. There's a variety of advantages and disadvantages associated with the small modular reactors, but all of this comes down to whether it's going to be economically viable, whether they're going to be pushed forward. And so as we started to look into the literature and understand what had been done, we really identified the need to have the improved fidelity in the modeling. And so, for example, one of the things that's proposed about small modular reactors is these are going to be stamped out in the factory. It's no longer one-off custom on-site development for new power plants. They're going to be stamped in a reactor and shipped to the actual location. But when you look at the economic modeling that's going on there, they're not including the factory costs associated with the construction of that. And so that's really, if you will, a hole in the armor. And so we went in and kind of looked into that. And so there's a lot going on here. This is a breakdown. There's a very thin pencil line, gray line across the top of these. That's the factory costs. It's really not very significant. So this is kind of firming up the armor. Across the bottom, I'll explain this quickly, are 4 different configurations for small modular reactors, 1, 2, 4, and 8. And then the 3 different bars correspond to if you're going to first build it just on site, not integrating a factory. The next one is the overnight capital cost associated with building the reactor in a factory. And then the last one is building the entire reactor and genset actually in that factory. So you continue step down in terms of what these costs are. So when you get out to the far end, approximately between $4,000 and $5,000 per kilowatt, that's competitive with large reactors, and it includes the factory costs. Now, one of the things we identified in terms of operation as being a huge gap in the technology, or in the modeling work, was regulatory fee costs. And so on the far right-hand side of this are large reactors. Large reactors, and on the vertical axis, is the percent fees being paid. And so large reactors pay between 0.8% and 3% of their annual profits to regulatory